In this video, we're going to talk about expanded octet molecules. These are molecules such as PCl5, where the central atom has more than an octet. If we look at this drawing that I just drew, we see that the phosphorus has 5 bonds. And each of those bonds has 2 electrons, so that means that that central phosphorus has 10 electrons surrounding it, thereby violating the octet rule and having an expanded octet. Why does this happen? Well, starting in the third period, atoms start to get access to their D sublevel. So even though phosphorus's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3, 3d0, because it has 0 electrons in its D sublevel of the third energy level, when phosphorus shares with other atoms, it can actually share into that D sublevel, because once the third energy level is occupied, the D sublevel of the third energy level is available. So basically, starting at phosphorus, and for all the non-metals that are larger than phosphorus that bond, they all have this ability to extend their octet. But when it comes to drawing these molecules, it's not really any harder than drawing the other molecules. We just follow the same steps. Let me show you how. Just like before, I start out by adding up the valence electrons in the molecule. Phosphorus has 5 valence electrons, and each of the chlorines have 7 valence electrons. This gives us a total of 40 valence electrons to use in our bonding structure. Just like before, we make phosphorus our central atom because it is the one that needs to get the most number of valence electrons. And then we go ahead and we just single bond all the other elements to that central atom, just like before. Those 5 bonds all have 2 electrons each, so that is 10 electrons that it takes to make those 5 bonds. So we still have 30 electrons remaining to add to the structure. We add them as lone pairs to the outside elements. Doing so is going to use up all 30 of those electrons, leaving us with none left over. Then we check to make sure everyone has at least an octet. If I look here, this chlorine has an octet, 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 and phosphorus in the center has at least an octet. In fact, it has 10. So this is the structure, and we're done. Let's try this one, SeF4. Again, we start by adding up all the valence electrons for each element in the molecule. Doing so, we see that this structure has 34 electrons in its bonding structure. We then single bond the fluorines around the central selenium. And we deduct the 8 electrons we used for those single bonds from our total, leaving us with 26 electrons still to be added to this structure. We add them to the elements on the outside first to fill their octet, and in doing so, we use up 24 electrons, leaving us with 2 electrons remaining. And while this may seem strange because everything in this structure currently has an octet, the fluorines all have octets and the selenium all have an octet. If you have 2 electrons remaining, that means they must go on the central atom. If you follow this procedure, you just always have to account for your electrons until you have none left over. The reason why we have these 2 electrons going onto the selenium is because selenium is, again, an octet extender. We don't expect you to be able to determine just by looking at the structure if you're going to have an extended octet. If you just follow the procedural steps of drawing your Lewis structure, you'll always come to the right structure as long as you are properly accounting for your electrons. Let's try another funky one, XeF2. Now you maybe you're saying to yourself, wait a second, xenon is a noble gas and it should not be able to bond. Well, it turns out that larger noble gases, they can be forced to bond when they're with a super electronegative element like fluorine. But again, we just follow the procedure. We add up the electrons. Now weirdly, in this case, xenon is going to be the central atom, and fluorine, because it's so electronegative, that's going to be on the outside. Draw our single bonds and deduct the 4 electrons that we use to make those single bonds. We then fill the octet of the outside elements first before we touch the inner. And if we look here, we get left over 6 electrons. Now where do those electrons go? Well, just like before, any remaining electrons go on the central atom. So when doing so, we see that xenon gets an extended octet because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 10 electrons surrounding that xenon. But that's okay. Just follow the procedure and you will arrive at the correct Lewis structure for each of these molecules.